Hello, Ted here, and welcome to another AINT308 demo. This time we're looking at assignment 2, task 4, and we're looking at a bit of stereo mapping. So we've been issued with 2 sketches and some collections of images. The first sketch is a calibration sketch, where we can take a collection of stereo images, so the 2 cameras locked in place, taking pictures of the same thing, of a checkerboard, and we can use the example sketch to calculate the transformations that we need to apply to both images to get them to line up so that any object is only offset horizontally, not vertically, between the 2 cameras. Once we have those files, we can plug them into the second example sketch, in which it takes those parameters that we've generated, takes a new set of images, this time of a box being held above a ruler at 10 centimetre increments, and applies those transformations we've just found to get 2 rectified images, of which we can then disparity map. So we can find the distance between 2 pixels of the 2 images, the offset between them. Knowing the FOV of the camera, we can figure out how far away something is. Now, we don't actually know the FOV of the camera in this instance, but we know the distance of the target, but we'll come to that in a second. So I'm only going to be showing one of the collections of images in this demo, and that is the known distances. There is a collection of unknown distances as well, however it's the same code, it does the same thing. So I don't feel the need to show it twice. So if we hop on over, we can start to get a look at what we're doing. So at the top we can see we have right and left images, respectively, of what we're seeing through the camera. You can see that quite clearly the box is in front of the camera on the right, whereas the box is to the right of the camera on the left. So we can look at the displacement between certain features, like the edge of the sticker and the edge of the sticker in the equivalent frame on the left, and figure out the difference in how far away it is from the left side of the image. And that we can show as what we call a disparity. We can have a look at the disparity we find here. So the further away from the left side of the image, when looking at the distance of a pixel, the same pixel in both images, so for example the P in Plymouth, is going to be a certain distance away from the edge of the right image, and in this case, further distance away from the edge of the left image. In this case, we know it's a large distance, so the disparity between the 2 is quite large, and so we can colour this pixel white. As you can see, part of the disparity map is black. Because of the way disparity mapping works, we search a region for the corresponding pixel. We end up with that search region at the beginning, where we can't shift backwards beyond the edge of the picture. So we can't use the information. There are ways around this where you can disparity map from the opposite direction, but that wasn't required in this example. It was asked and it wasn't required, so to save time it hasn't been done. From this disparity map there is a linear relationship, there is a constant relationship, not to get confused, with the distance away from the camera. Now in this case this was found experimentally as detailed in the report. So it turns out that the distance of an object is inversely proportional, in my case to a factor of 3,900 to the distance. So the distance away from the camera equals 3,900 over the disparity, so 0 to 255 in this instance. And that will give us the distance in centimetres between 0 and 255. So applying that equation to each pixel in the image, we end up with this glorious mess, in which the close objects are represented by grey and black dots, pixels, and further away is represented by white. In order to automate my code a little bit, this will start to make more sense in a minute when we see the pictures moving away, I've created this search region that always is in front of the target box. So if you look at the Plymouth University box up here, that little red box will always stay over the box. And we search over that red box and we find the most common pixel colour in it. And that is what we take as the distance away from the camera. So we get rid of these little white speckles that are caused by perhaps reflections or dirt here and there. And finally we have the console. Now in this console we're going to be able to see the distance to each target printed out. So here we can see that it's a loaded image pair 0, and the value it's found the most in that little search box is 30, so 30 centimeters, and it finished in 135 milliseconds. So reasonably speedy. It's about 7 frames a second-ish, I think. So not too shabby. The range of known images goes from 30 to 150 centimeters in 10 centimeter increments. So we're bang on the money for the first image. I can step to the next image here on my keyboard, so you can see the box has moved further away. The disparity map has become different because now the difference between the distances in the two windows are changed. Move my mouse out of the way. And we can see that search window again is still over the box. We're still getting distances between them. We can see that the console has now said loaded image pair 1, and the most search distance, so the modal value in that search square, is 40. Took 2 milliseconds longer, but again we're bang on the money with that one. 40 centimeters away, the image 2 representing 4 centimeters, and this continues on. So again, looking at image 3, which should be 50 centimeters, we're getting 50 centimeters in the console, and we can just keep doing this, looking at the values, going up in increments of 10, 60. Here is our first deviation. We should have 70 centimeters. We have 69 centimeters. So either there's a little bit of error in the measurement, perhaps it was actually 69 centimeters in the measurement, but it was recorded as 70. So our program is correct. Or there is some slight deviation in the inverse relationship for these cameras. Perhaps there's some minor differentiation in the parameters we've used to correct the image that means that it's slightly off. But being only a centimetre off, that is rounded as well. So we're anywhere between 1.5 and half a centimetre off, which is still pretty good considering. That's a pretty good accuracy. We can step forward once again. This time we still have an error of 1 centimetre in there at 79 in the console. Again, it's taking about 135 milliseconds, so it's pretty consistent for each frame. So that allows us to have a nice estimation of how long our program will take to run. This time a little bit more differentiation, 2 centimeters. So it seems the further we get away from the camera, the more error is introduced. Again, 2 centimeters, not too shabby. Noticing once again, we're back to bang on, 100 centimeters. And coming to the end now, 110 centimeters, 2 millimeters off, 120 centimeters, 1 millimeter over this time, 130 centimeters, sorry, in the previous instance I meant centimeters. We can see we're still on the money. Definitely a little bit more now. We're reaching the outer ranges of this calibration. As you can see, there's a lot of noise in the image, so perhaps some extra filtering could help reduce that in future. We're looking at 144 centimeters on that one, as opposed to 140, and then our final result, 150 centimeters. Hello again, Future Ted here. Camera died. I was just saying that if we look at how the known images were taken, they were taken by eye above a metre rule. So perhaps there's some error in this. If you're measuring to the nearest 10 centimetres, it's going to be a maximum of 5 centimetres. So the maximum error in the stereo mapper is going to be our maximum error, which was 4 centimetres, plus the possible observer error, which is 9 centimetres. But that's an extreme case. As we can see, 54% of the time, we were bang on the money. So the real error is a lot less than this. But have a look at the report for details. That's my demo of task 4. I hope you stay safe. Much love to you all. See you next time.